Okay. So we're gonna spend today talking about cubic spline, and then we're gonna move on to numeric differentiation. One student has emailed me, and presumably the rest of you would be interested in this too. So has I didn't do well on the midterm, and can the final count for more? Or some version of this. So what I have done, as you probably know from my announcement, the test was out of 60. And the performance was not very good, and I have now lowered the total down to 50. So whatever mark you got, they'll be out of 50 and not out of 60. This actually does mean that several people have more than 100%. Okay, so there was several people who had a mark over 50 anyway. Okay, so that would be where you would want to be looking at moving yourself into that category. So that brings the average to somewhere in the mid 50s. Like percent, or percentage wise, right? So if the average from before was in the 40s and now it's in the 50s from that change. Okay, so that's point one. Point two is I actually used a midterm very similar to this in 2015. The average when I did that 7 years ago was 65. That indicates to me we've had a little bit of a mishap, possibly during the pandemic, right? I think there's some number of you during the pandemic who didn't learn perhaps in what I would say the proper way, in that you were understanding the material and grasping the concepts. Instead, I think it was turned in the pandemic more to like, what type of questions will be on the exam? How do I do that exact type of question? And I'll just remember how to do that, potentially using my notes and other Discord group or something else during the exam to help out with that. And that has resulted in less learning for some people. It is clear that some of you from the answers I saw on your test have extremely weak prerequisite skills. I don't know how for you to fix that, except for when you don't know how to do something that relies on something that you learned in high school, that you then have to stop right then and say, okay, now I have to spend 2 hours of my life reviewing what the rules of logarithms are. Okay, for example, on that, you have a algorithm that you expect this type of behavior. Okay, and you plot log time versus log n. And you want to know, did I get this type of behavior? That was the question, right? You have your time proportional to 8n squared. Your log of your time is proportional to your log of your 8n squared. So many of you did not even get to here, but let's just say that you got to there. Many of you could not do this, despite the fact that this is what we did on 2 computing assignments, despite the fact these are basic log rules from grade 12. So if this is you, not to be too hostile here, if this is you and you cannot take this and put it like this and then say, oh, I see, if I plot log t versus log n, I will see a slope of 2 and a y-intercept of 8, and then I'll know I got 8n squared performance. That is the question. That was the question, right? Exactly what we did versus time versus matrix size with Gaussian elimination. We did a log-log plot. This is why we did the log-log plot, so we can look at the slope and see the exponent. Okay, many of you did, the people who got here, so many of you did stuff like, I don't know, 2n log 8. 16 log n. Some version of this that indicates no understanding of the rules of log. That is not what we're doing here. Period. Like, this is something you just have to, you already should know. And if that's you, or if there's other things like this on your thing, you have to take the time to fix it. I don't know how much time that will take. It just depends on where you're at. Okay, so that, from my perception, is some portion of the problem. There's been some loss during the time of chaos, right? Not necessarily anybody's fault in some sense either. We've all had different losses of different sorts. only thing we can do now is fix it. The next thing, I will say regarding what will be, well, so now it's not so bad now that I've cut 10 marks off the top. But then what I will do, and I will do this for everybody, and I do it blind, so I don't know your name when I'm doing this. At the end of the day, I'm gonna calculate a mark for you. I'm just gonna put some rough marks down here. Like, I'm gonna calculate exactly according to my grade scheme, okay? Pardon me? Well, yeah, I mean, if you're expecting this and you plot this, then you expect that you would have a line and you would look at the line and you'd go, the slope of my line will be 2 and my y-intercept will be 8. And I'll know that I got what I expected. 08 n squared. That is the whole reason to do that. That's exactly why we did the Gaussian elimination. We have Gaussian elimination. We were like here, right? And we went and plotted all those matrices against the time. We did a log plot, and we tried to observe the slope of 3. It's not. Some of you just said, it will be working if I see a line. And it's like, okay, at least you understood that it was going to be linear when you did this. But I mean, if the slope is 5, it's not working well. If the slope is 1, it's also not working well. The actual slope is, that's the most important criteria, is the slope. It's telling you what the exponent is, right? Yeah. Yep. Yep. I'm about to head into that. Okay. So at the end of the day, well, whatever it is, I've forgotten the exact number, but we have some percentage on everything, right? Like the final is, I think, is it 40% or something? Okay, 40%. Then we have a midterm. Okay, you guys have spent more time doing this than learning the material. Okay, we have quizzes. 20. We have a proceeding. Okay, 20. So, and then there's been a variety of people who've been sick, and I've been moving them out for quite on. So, like if they missed one quiz, that went on to the final. For some people, the final is going to be a little bit more, right? Or whatever they missed. Okay, so I will calculate your number, and this midterm will be out of 50, like I said. So you calculate your percentage out of 50, not out of 60. Okay. Then I will do this calculation for each and every one of you. I will get a list of numbers. It will look like something like this. I will go down, right? Somewhere, we'll just keep going down, whatever, and there'll be something like this. Okay, whatever. There'll be a list of numbers. Okay, then, so that will be exactly computed according to this. Computed. Then right beside will be your final exact score. I don't know. There'll be some number that will be a final exact score. Right beside. Okay, then I will take the standard grade breaks. Okay, how this goes, right? It goes down like this. Whatever, what is the next one? 85 to 90, right? Like that. Okay, I will look at this little list. I may adjust these numbers slightly, and I mean slightly, no more than 2 or 3%. Okay. So just slight adjustment on the grade break. Now the grade breaks are selected. I draw them in. Whatever. A plus, A plus will not go down to A, whatever. Then these guys are in the A minus blob, like that. Okay. And then I look. Let me make one that's maybe a bit more representative of what would happen. I don't know. We got somebody who has an overall average of like 60.2 and got 85 on the final. And this overall average, that's some, I don't know, C or something. Then I look and I'm like, hey, look. They would have got with 85. They would have gotten them if I just look at this number, they would have done a lot better, right? They wouldn't have gotten a C, they would have got whatever, a B plus or something, right? Huh? Well, maybe, right? At first I'm going to be saying this, right? But yes, it won't be any lower than an A. Most times, right, the minus sign, but ready into it. Okay. A minus. Okay. Ridiculous. Okay, yes, they would have got an A minus. but no, overall, they got 60.2. Then I look at, then I stop, like, so the people who just fall into the same bucket on both, they're done. I'm done with them. Okay. Okay. The people who fall into a bucket, okay, there's two ways this can happen. They got an overall of 60 and their final exam was 40. Also, that's actually more. Okay, there's two possibilities. There's the two possibilities here. When I stop at this person, whose final exam score is way different from their overall score. One is it's a lot lower, and one is it's a lot higher, right? That's two ways of being outside the bucket, right? Okay, if you're way lower, like this, I just leave you alone. I don't lower you down because you can crap here on the bottom. Okay, so when you ask for one direction, you have to consider that the other direction is also possible, right? If you guys scale the class, but I can scale it down. If everybody gets 80, I'll scale it down to 60. How's that? Right? Okay, so I'm not doing that. So I'm saying if you do lousier on the final like that, and you're in the 60.2 thing, whatever that is, that's the letter grade you get. Okay, not scaling down. What do you show me at the end of the time, at the end of the semester, you really don't know what's going on. I'm still gonna overlook that. Okay. If you were here at the end of the semester showing you I can't understand. But I have to hit that. Then I stop for this person right here, and I look back at every single thing you did. You had a chance to score those points, but you didn't. You had a chance to take the quiz. So nothing. You stay right here. If I look back, and I say, okay, let's first get all the quizzes, we did all the and that's right to mark down well below what their thing is. I look at that and I make a judgment and I change this somewhere up. I don't generally go the whole way. Like I'm not just like I can't say you're not the same as the person who got whatever it is, 85 on everything. They're not. Right? The person who got lower on a bunch of stuff and got 85 in the final. So I don't bump you the whole way up, but I bump the letter grade up at least to the next one above, maybe two. You're not dead in the water if you got the mark in the midterm that you think is terrible, right? You're not necessarily going to fail the course. And further, for the people who are down here, where their overall average is like 45 or something, where they would get a B or an F. And then this number is something like 65, like they made a solid pass in the final pass. I'm talking about this. My recommendation, my field is graded is not the first, but we should really seriously think about not taking the next step of the life of it. Because your understanding is confused, right? And I may be sounding like mildly hostile, like that, but I do actually say, and I don't have to do this one, I feel it's the same community. Now, when it's control option, it's not just and what it's doing on the spot, and then it's still not to be different. So we have to look like doing how to practice very long and stuff, using it to get more. Okay, so when that happens, what do you do? Last time this one, you go about it to detail. When you get about the student, you see off the daily life. Because you get it, so you have to do it last week and like the student really like it. It would be better if you money on the student. It really actually. He had an experience with getting his mind to calculus one. He then failed calculus two. And I don't know what mechanism he decided, you know what, I just need to take calculus one again. Which he did not have to do. And he did that. Then he came to calculus two again. He got an A. He's like, okay, the whole problem is from before. And this is the problem of pushing people along. Right? It's like, hopefully you didn't quite get that, but we'll just kind of scale up and everybody will move along. That strategy does not work well, actually, and at some point it will just melt down for you. So that is my my philosophy here. The other thing that you should be aware of is SFU. So some of you, of course, you can about it. That was for 5 years, but in the end, that was constant. What do you do? And so what family are you serving? And that's it, for the life. And if you go in there and you say, oh, actually, we teach you numerical analysis, but what we're doing now is we're just getting them to do these little basic little baby little problems, and we're not teaching any of this other stuff. They're like, well, actually, that's not good enough, right? No accreditation. So that would be a horrible outcome for anybody with a degree from this university would be to cover accreditation removed, right? That does actually happen. So it's not a random standard in this sense, where it's like, oh, we're just trying to make things hostile, but we do have same thing in medical school has standards too. From someone graduating somebody all on a curve and like staggering around, like cutting out the wrong parts. Like it's not a good strategy, right? So there's that, and then there's also the reputation of the graduates to consider, the people that came before you, the people that when a bunch of applications land at a at whatever company it is you're trying to work for. I worked in engineering for 12 years. Okay, and so I mean, regularly, some people do like, here's the application for the job. We're all the ones from the university. Graduate studies stuff. We're not hiring. We're not even to consider them. They actually, some of them are probably good, but we can no longer, after you've hired 3 or 4 people from a university, you're like, those people are not very well trained. Standards too low. We're not going to look at them anymore. So you don't want to be getting a degree from a university where a reputation gets established at some point out in the real world of having low standards. Because that means even if you're really good, you kind of get tarnished with that brush and right? So I mean, we hearing from you, I imagine if that was a third person, you're gonna look how it is, and you're like, okay, let's take a look at these from let's look at these from the village, these from UBC. Let's look at, and you want to be high on that list, right? And so it matters. I mean, we all know this, right? It's better to go to Caltech than it is to go to, I don't know, Podunk, Iowa, right? But the results is better. So we want to be a bit careful about how we discuss this stuff. I just want that kind of, I want you to have that context in your head too, rather than say, we just want to get a good grade. Like, I understand you want to feel good, and I understand you want to do well, and I understand you're applying for things, et cetera, et cetera. You want to make it to your program. I am aware of that, but I just want to have that context there as well. And that is my procedure of what I'm speaking. Okay, you guys are free to say something on it, and then we'll talk for it. Yep. Yep. Right. Yep. That is that is something. So the comment is, you know, you can't do part A and then part B and D and meltdown. So I will take a look at the midterm action with that in mind and sort of see whether I believe that to be true. There are certainly some where, you know, you can't do the LU factorization, then you can't find a determinant very easily, for sure. So yeah, that's it. That can happen, right? So I will attempt to make it so that the sometimes there's some questions that are just flat out hard to do if you can't, like, there's some things that you just can't, like, I don't know, if you can't say do polynomial interpolation, then you can't say you know, well, we're going to do numeric differentiation today. So one way of doing a numeric differentiation is to recognize that it's easy to differentiate polynomials. So if you have a function that you want to differentiate that's complicated, like, forget it, I'm not going to differentiate that function at all. I'm going to just do a polynomial interpolation, differentiate that, and use that instead. So now, if I ask a question about that, and you're like, I can't do polynomial interpolation, it's true, you'll be dead in the water. Like, I don't know what to say. It's building up. So okay, I got that. Okay, other comment. Yep. Correct. Yeah. Yeah, no, there's no way. Points. No chance. We wouldn't be here. Yeah. Okay. Other comment. All right, let's focus on getting as much of this stuff learned as possible. And to do that, we are going to, let me be right up front about this. For sure, I'm gonna ask you to construct a cubic spline on the final exam, right? What, absolutely for sure. Well, let's do it with a 98% confidence interval, because this is a important topic. I've tested before, and there's good reason why the cubic spline is used. Okay, so first we're gonna do is figure out how to do it, and then we are going to we're going to talk about why it's used all the time. Okay, so here we are. We've got 3 data points, and we're going to put a cubic spline, and we're going to put a natural cubic spline. Okay, so there's 3 types of cubic splines. There's the not a knot, there's the natural, and there's the clamp. That's the boundary conditions. You have to know what the differences between them are. Okay, we got to do a natural cubic spline through the data points. We've got 3 data points. So how many cubics do we need? Huh? I hear 2 answers, 2 or 3. 2. We need 2 cubics, right? We have 2 intervals. So we're looking at a situation where we've got 3 data points, and we're going to put 1 spline here and 1 spline here. Okay. 2 cubics. So we're going to write out what those are. There's cubic 1. I'm going to call it S naught. It's going to be A naught plus B naught S plus B naught S squared plus B naught S squared. That's going to be in the interval 0, 1. Okay, that is going from 0 to 1. That's the, these are my x coordinates, 0, 1, and 2. And my y coordinates, well, it's not going to give this graph, but this is 0. And then this is 2. And then this is 1. Here's my two difference. So that's the interval 0, 1. And then we're going to have a second cubic, which we're going to use in the interval between 1 and 2. And we'll take it A1 plus C1 X plus C1 X squared plus C1 X cubed. So the interval 1 to 2. How many unknowns? How many things do we have to figure out to do this? 8, right? All these A, B, C's, and D's, right? That's what we don't know. We've got 2 cubics. And we want to know exactly which cubics there are. We have to specify A, B, C, and D. On the unknown. Answer A. Okay. So step 1, we want it to interpolate. Okay, that is step 1. We want it to interpolate. That means that S0 of 0 has to be 1. 1, right? That's this data point right here. And it also means that S0 of 1 has to be 1. 2, right? That makes the first polynomial interpolate on this region. That's one of the, and then we do the same thing with S1. S1 of 1 also is 2. Because that guy starts here in the second interval. So interpolate this first 2 seconds. And then we also have that S1 of 2 is 1. All right, I'll go into the let us write out the equations that we get from there. What equation do I get from that regarding my unknown? A naught, sorry? A naught is 1, absolutely. A naught is 1. There we go. Okay, how am I doing now? I'm saying, well, look, when x is 0, y is 1. So I'm plugging that in right here. Plugging in x equals to 0. The value I'm doing the function value. Okay, so I get that from that one. Now I'm going to take a look. That's one equation. What equation do I get from here? S01 has to be 2. What does that tell me about? A, B, C, and D, or any of them. The sum is? Thank you, the sum is 2. A naught plus B naught plus C naught plus C naught is equal to 2. Okay, that is that. Now I'm moving to this side. What does that tell me about my unknown, my 8 unknown? What equation do I get from this guy here? I get A1 plus C1 plus C1 plus C1 is equal to 2. That's 1 as 1. Oh. And then I'm going to actually stop this computer and think to myself, oh, yeah. I haven't done anything wrong actually, but I see immediately how I can make it much faster. I'm just going to accept it. Okay. I'm going to stop. I'm going to show you something. And then I'm going to change this slightly. So we can get, this is correct. There's nothing wrong with this. But let me show you something. You will notice that our first guy here is 0. And it was really nice when we had that S0 was 1, because it immediately allowed us to find out one of our 8. Right? That's a nice feature. So when I write out S1 of X, the second polynomial, I'm noticing that the first data point that applies to is this guy, and I'm in this range right here. Okay. So instead of writing this polynomial like this, it doesn't matter if you do it like this, okay? You can see along with the same procedure, but instead, I'm going to do this. I'm going to write it like a little bit. Okay. When I find A1, B1, and C1, and D1 here, will I get the same polynomial? Or not? That will, right? Doesn't matter. Pardon? Yeah, it's just a shift, and it doesn't matter. Like all the numbers will come. This is a third degree polynomial. I can write any third degree polynomial, and these little numbers basically are here. That's because I'm already thinking of the 3 when I wrote down the 1. Okay. This has a nice feature now that when I do this evaluation, S1 of 2 is equal to 2. What does that now tell me? Well, my confidence. A1 is 2, absolutely. This is just so that we don't have to solve such a huge difference in your equation. Okay, now let's move to this guy right here. That tells me what? This guy. What equation do I get there now? Yeah. Yep. Yeah, we're just saying we're gonna put a third degree polynomial through those 2 points. It's a unique. Well, if we're gonna put a third degree polynomial through those 2 points, and given the interpolated condition, the derivative condition, and boundary condition, it's a unique polynomial. If I write it like this, okay, try to make it. I'll try to make this more clear if I can. Like, what if I was just to go like this? Don't really focus on doing it, but okay, well. No, I think you do it wrong. How am I doing so far? I'm expanding it. Now I don't want to expand the next one. So what am I doing? 1, 2, 3, 1, huh? 2, 3, 1. 1, 2, 3, 1. 1, 2, 3, 1. Okay, you see what's happening here? This polynomial I've written out here, A1, and then there's B1x, and there's C1x squared, and there's B1x cubed. And then there's, let's just look at this B1 here, minus B1. I can just combine this with the A1, and that would have to be over here. Like it's the same, it doesn't matter. There's degree polynomial. Maybe let me just do it in a quadratic. So I really want you to grasp this idea. And then just do it linearly. There, there's a line. Here's another line. Okay, both of them are lines. Right? So it's y1, y2. And y2. Okay. I just took this and expanded it down to here. Okay. And then I'm this one below. So this, if I make those equal, same line. I can figure out what they are. I can figure out what they are this way, or I can figure out what they are this way, and either way, this relationship will hold. My new constants will be A1 will be the A2 minus B2, and B1 and B2 will be the same. Do the same thing with the cubic. I just extract it and multiply it all out and combine it. That's what I'm saying. Yeah, I'm saying if there's two cubics, that's right. I'm saying what was wrong before, and you can set it up however you want. You can set up your cubics to x's here, or you could set up your second cubic like this, which is not what I want to do because it makes solving a linear system a lot faster. All right, so now we're back here with my new cubic here, trying to identify what that's one of two equals one tells me. Very quietly, very good. Thank you. That's what I heard, right? Yep. So we're just trying to, we don't care, like what we're gonna do at the end of the day, we're gonna figure out what these things are, like that. And we're gonna figure out what these things are. And then we are going to report that as a phone number. If you wanna multiply it all, then go ahead. I don't want to do that, so it doesn't matter. There's the phone number, that's what we find, there it is. Right, and it's the same thing, well, I mean, it's not exactly the same thing, as words in that case, but with the Lagrange stuff, you don't want to start like multiplying yourself by like there's no purpose for this. Okay, so we've got that A1 is 1, A0 is 1, so that now tells me that here B naught plus B naught plus B naught is 1. And then we have here also we have that A1 is 2. That tells me that B1 plus C1 plus C1 is equal to minus 1. So come out of that, of the interpolating situation, two equations, and fix on that. All right, so now we do the calculations on the derivative. So that our next step is to the derivative condition. The derivative conditions are to match the derivative of the condition at the interpolation where these two functions go. Okay, I'm going to go back to my graph. So we're now talking about this point right here. We have one fixed line there, one fixed there, one we will still feel a slight spot. And then, you know, we're going to match the first and second derivatives because we can't match more of them because we don't have enough to do the freedom. Okay, so we need to know then that S0 prime at 1 is going to be equal to S1 prime at 1. So please try not to, like, so, I think a fatal flaw is you try to memorize. So instead of you thinking to yourself, okay, I'm thinking about the derivative condition, why am I doing that? And then being able to write this out because it's easy to plug up and then one of the derivative condition. Other derivative condition is to match the second derivative at that same point. All right, so now we would have to actually know what the derivatives and functions are. We have our two functions. We have S0 of x is A naught of B naught x plus C naught x squared plus B naught x cubed. So S0 prime of x is B naught plus 2 C naught x plus 3 B naught x squared. We can then take also this second derivative. That is going to be 2 C naught plus 6 C naught x. Let's do the same thing for S1. When we take the derivative, and we get C1, and 1 times the derivative, 1 times is 1, plus 2, 3, 1, plus the derivative, the inside is 1, times the derivative, inside. I'll take the second derivative. I get C1 plus 1 plus I'm thinking this is B1x and then minus B1 that's a constant. So that's doesn't with the constant 0. B1x plus B2 6 B1. Sure. All right, so I take the derivative and then I do these two evaluations and I make them equal. Do I make a mistake? Possible. Hang on. Look at this. This should be S1, right? E1. What I do wrong? Now look at the first derivative. The derivative of that is zero. The derivative of that is, oh, that is b. One. Thank you. That's that. Where I have a token of, hang on. The derivative of that is b1. The derivative of b1 times minus 1 is 0. The derivative of this is c1 times 2 times. Pardon me? Oh, yeah, then the b1 disappears here. That's right. Follow along the straight. Yep. Okay. Are we okay now? Okay. All right. Thank you for that. Okay. So now we're going to substitute into the newly correct function, the derivative of the. I got b naught plus 2b naught plus 3b naught is equal to b1. That's this guy. Then I do the second derivative, this guy here. I find out that 2b naught plus 6b naught has got to be equal to 2b naught. I still have, I have figured out two of my 8 conditions. And now I've got 4 equations for my remaining 6 unknowns. And also note something here. This is I was about to say, I'm apologize to say, is that independent of the data or not? Yes, it is, right? It's only depending on the node. We didn't use Y at all, right? This is independent of the Y value for the data, right? It's only dependent on the node. Okay, so next thing, so we first make it appropriately, then we make it match the derivative condition, and then we look at the question, and we see it's a natural cubic line. That is the boundary condition. So we're gonna match now. We're gonna do the proper boundary condition. And what is the natural boundary condition is the natural one is the easiest one to do. That is to set the second derivative to 0 at the 2 endpoints. Now, like to put our pause. Okay, that is then going to give us, I evaluate those functions like that. And I get that 2c0 is 0, and that 2c1 plus 6c1 is 0. I have now another 2 equations. This is exactly, I'm glad you asked this question, right? This is exactly what you want to get clear in your head what you're doing. Why would I check the derivative conditions here? It's really smart that you asked that. Okay, let us just go here and imagine a cubic spline with more data flow. Okay, there. How many functions how many qubits am I going to have to do this one? 4. There's 4 intervals, right? Okay. At which nodes am I going to match the derivative? 1. Right. Because I'm trying to make it smooth. At which nodes do I care about the boundary condition? So, yeah, right. Those are the boundary conditions, and then the other one. Yep. Okay, we're proceeding with this example. We now have 6 equations and 6 unknowns. Now, actually, it's not as bad as it looks, but you have 6 equations and 6 unknowns. You solve. I would like you to do this in an example. Do this. Think to yourself, I'm gonna do one of these things. I'm gonna all the equations, and then I'm going to figure out what the unknowns are. And we know how to do 6 equations in 6 unknowns. And this is the minimum number you're gonna ever have on a given one, right? This is the smallest number of data points you can have, 6. If you have 2, you don't have even 2 functions, okay? And you have 1. Okay, so you do this, and you will observe that you find out this, and you will write it like this, You're like, my interpolating function, my cubic spline, looks like this. 1 plus 3x over 2 minus x cubed over 2, and 2 minus 3 half x minus 1 squared, plus 1 half x minus 1 cubed. And if I'm asked to use this thing in the interval between 0 and 1, I will use this one. And if I'm asked to use it between the interval 1 to 2, I will use this. But I basically now, so this is when you solve the 6 equations and 6 unknowns, this right here is A0. This right here turns out to be A1. A2 is clearly 0. And then this guy here turns out to be A3. 0. Yep. And this thing here is A1. This guy here is B1. No, this one is B2. And then this one is B2. Other questions you want to ask about this? Yeah. That's a good question. So is it possible that you would try to do 6 equations and 6 unknowns and find out there's no solution? No. Because you think about the physical situation. You can clearly put a cubic through that. You can clearly put a cubic through that. End of story. It's not going to be like not solvable. Yep. Yes. No, think about what B1 is. B1 is on the linear term. B1 is here. B1 is 0. And here, A2 is 0. Yep. Okay. We will continue with the cubic spline, and then we will start the numeric differentiation on Friday. Not very high. Make sure I catch this one.